Okay, guys. This video is about another chapter about nuclear physics. Is what we call mass energy equivalence. Okay, so this one actually involves the very famous equation in physics. Possibly you have seen that before, but I bet you don't understand the meaning of it. Okay, so the so-called mass energy equivalence is this formula. Have you ever seen that before? Right, so we're going to introduce this formula today. Alright, so here's the notes. Alright. Before we go to that famous formula, first we need to introduce a unit which is called electron volts. So first of all, what kind of unit it is for electron volts? You see, electron is something to do with electricity, right? And volts, possibly you have learned that. So you know that volts means voltage, right? So it's about like our battery cells. Normally when we call the magnitude, okay, of the battery, we use voltage. Okay, so electron, you know what it means. But actually, the whole thing, electron volts, is a unit of energy. Okay, so it's a unit of energy. Okay, so what's the definition of an electron volt? Electron volt is the amount of work done. Okay, so that phrase possibly is quite unfamiliar for you. So work done means energy transfer. Okay, possibly that would be easier in moving a single electron through a potential difference of 1 volt. Okay, you might imagine the things like this. So if I have a pair of electrodes, okay, and I connect that two electrodes to a battery. Okay, so you know battery, you got positive terminals and negative terminals, and that battery, the voltage of that battery is 1 volt. Okay, so for the left hand, what we call a plate, okay, is positive because it's connected to positive terminal, and on the other hand, there's a negative terminal. All right, so now if I put an electron right here, so this electron is at rest, so it's stationary. Then you put that between the two electric plates. The negative side will repel the electron because the electron is negative, and the positive side of the electrodes will attract that electrons because positive and negative, they attract each other, right? So what happens then? So we will expect that electron will move towards the positive plates, and in the process, okay, its speed must be increased. So after it reach here, so the electron becomes very energetic. It pick up some speed, right? So it becomes high speed right here. Okay, so the energy gain, or to be more precise, the kinetic energy gain in the process is what we call 1 evolt. Okay, so is 1 evolt a large amount of energy or a very small amount of energy? Actually, it's a small amount of energy. Why? Although electron pick up high speed, but you know that the electron has very small mass. So even its speed is very high, its overall kinetic energy, still remember that's kinetic energy, right? So kinetic energy, what we call Ke, the formula for kinetic energy, half mv squared. Okay, so since the mass is very small, even though you have a high speed, the overall kinetic energy is very small. Okay, so how small it is? So when you turn that 1 eV, okay, into 1 electron volt into joule, our conventional units for energy is 1.602 times 10 to the power minus 19. You need to appreciate that minus 19 is really a small number in the power, right? So remember that's the first thing you need to understand. 1 eV is such a small unit, such a small amount of energy, all right? eV is used to describe energy of small magnitude, all right? In nuclear physics, since eV is too small, sometimes we need to magnify that a little bit. Sometimes in physics, we use 1 mega eV. Mega means million. Sometimes with giga, okay, that means billion. Sometimes with tera, okay, so that's the short form. That's tera, that's giga. Okay, that's mega. Okay, so 1 tera eV means 1 times 10 to the power 12 eV. Okay, but the most common one will be this one, 1 mega eV. All right, so that's what we normally use. Okay, turn to next page. Okay, let's see. So this is an example from the book. All right. Radium-226 is a radioisotope that decays into radon-222 via alpha radiation. Okay, so there are a few concepts you need to review. Decays means you release your energy in terms of high energy particles or electromagnetic wave, and it becomes more stable. All right, and through alpha radiation. So alpha particle is this one, is helium, right? And so that's the reaction. Okay, so for all the nuclear reaction, we know that the purpose of a nuclear reaction is to release energy. Okay, so let's say if 4.934 mega eV of energy is released from radium-226, stay in joules. Okay, so you need to rewrite the energy into joules. Okay, how could we do that? Okay, remember, okay, 1 eV equals times 10 to the power what? So remember, we just see before, right? 10 to the power minus 19 joule. Okay, so now you got 4.934 mega eV. Okay, how could you convert that into joule? Okay, so it should be okay for you guys. Okay, so there are two things you need to convert. First, what's that letter means? Mega. Mega means million times 10 to the power 6. Okay, and then eV. eV means 1.607 times this one, joule. Okay, so use your calculator and you will get the answer 7.904 times 10 to the power minus 13 joule. Okay, so in this chapter, normally we will use the numbers with a greater number of significant figures. Okay, so normally in physics we use 3 significant figures, but here we use 4. Okay, the reason is in the calculation of nuclear physics, you need to be more precise. All right. Okay, so boy, if now I got that many of nuclei of radium-226 to do nuclear decay, determine the amount of energy that will be released in eV and in joules. Okay, so basically you need to calculate amount of energy in evolts or in joules. Okay, and there are that many nuclei. Okay, so how could we calculate that? Okay, so we know that one nuclei, so that's one nucleus. If one nucleus of radium release that amount of energy we have calculated, so one nucleus of nucleus release this amount of energy. All right, so how about 6.80 times 10 to the power 24 nuclei together to release energy, right? So how much energy can you see? All right, so in terms of evolts, we're going to do this one. 6.80 times the energy released by one nuclei. Okay, so we just multiply them. All right, so by doing so, you will have 3.355 times 10 to the power 25 mega evolt. Okay, is that okay for this answer? No, because the answer must be evolt. Okay, so you need to write that mega into 10 to the power 6. Okay, so in the end, the answer would be this one. That all right? Okay, but then you have to answer in joules. Okay, in joules. Okay, so the energy would be this one times 1.607 is this one, right? Okay, and you will see the answer would be 5.37. Okay, that's it. Okay, no problem. Okay, if you you have doubts, you got something you are not quite sure about, you could stop the video and rewind to watch it again. All right. Okay, so that's basically the first example. Okay, here is an example for yourself. Okay, so please do it as homework and send photos to homework folder in the OneNote. Okay, in OneNote. Thank you. All right, you need to do this one. Thanks. Okay, let's go to another one. Okay, let's talk about artificial transmutation. First, we need to understand what do we mean by transmutation. Okay, we have learned that before, but possibly we might use other words. For example, we might use nuclear reactions or nuclear decays, right? But actually, all these things could be transmutation. So transmutation has a very clear definition, which is when you have nuclear reaction, there must be daughter nucleus and its parent nucleus, right? So nuclear transmutation happens when the daughter nucleus and the parent nucleus is different in terms of an element. Sorry, is that not that clear here? I think I missed something. Okay, in nuclear is different element is a different element to its parent nucleus. They must be different elements. For example, in gamma decay, since daughter nucleus and the parent nucleus are of the same nucleus, they are not transmutation, right? Transmutation must happen when the daughter nucleus and the parent nucleus are different elements. All right? Okay. Okay. So let's see. And there are two types of transmutation. The first type is natural nuclear transmutation. The other type is artificial. Okay, for natural nuclear transmutation, there are many examples. For example, okay, alpha decays. All alpha decays. Okay, the parent nucleus will change into another element as daughter nucleus. So alpha decay must be a natural nuclear transmutation. And beta decays. Beta decays include beta plus and beta minus decay. Both you see the change in the atomic number. So that means the daughter and the parents are different elements. Okay, but gamma decay is not nuclear transmutation. Remember that, because in gamma decay, no change in the atomic number. So that means they are still the same elements. Okay. Example of artificial nuclear transmutation. Okay, there are many artificial nuclear transmutation as well, but the famous one would be fission. Okay, so we're going to learn fission, I think, in lesson 22. So we haven't learned that yet. So in lesson 22, we're going to learn nuclear fission. Okay. And also this one is an artificial transmutation. Why? Because you see, you use an alpha particle to collide with nitrogen. That can't happen naturally, right? Because alpha particles are positive and the nucleus of nitrogen is also positive. So without very high energy, these two cannot collide with each other. So this process must be artificial. Okay. All right. So you need to know the difference between artificial and also the natural one. Okay. So let's see some example here. All right. So that's another example from the book. But the book is a bit confusion. Actually, in the book, the example they write the answer right in the picture. So I kind of delete the answer from the question. So actually, we got something to think about. Okay, the stable isotope cobalt 59 is bombarded with neutron to produce an unstable isotope that is used in nuclear medicine. Right, the diagram below shows the particles involved in the creation of cobalt-60. All right, okay, so basically you see the diagram, and also it says very clearly it's about a neutron bombarded by the neutron. Okay, all right, so how could we write a full nuclear equation? So what do we mean by full? Okay, full nuclear reaction means you need to know the symbol of the element symbol with atomic number and mass number. Okay, so remember 59 here is the mass number, and so is 60. They are both mass number, so we don't know yet the atomic number, right? So where can we get the atomic number? Okay, so first you need to, for the full nuclear reaction, you need atomic number and mass number. Okay, so you need to track the periodic table for the atomic number. Okay, let's have a look at the periodic table. Okay, where is it? So we need to find cobalt, CO. Okay, here it is. Okay, so okay, so where is it? Where is atomic number? Should be 27, isn't it? Okay, so we know that cobalt, the atomic number is 27. All right, so we can write the full nuclear equation now. Okay, so that's CO. Remember that atomic number should be here, and you got 59 here. Okay, and it's strike um, striken by a neutron, right? So the neutron should be on the product. On the reactant side. So these two are reactants. Okay. So do you still remember the atomic symbol for neutron? Remember neutron, the atomic number should be 0 because there's no proton in a neutron. Okay. All right. And of course, it got one mass number because it's a neutron. Okay. Then what it becomes? It becomes cobalt 60. All right. So okay. Okay. So in this case, whether this is really a artificial transmutation. Okay, you might argue that cobalt 59 and cobalt 60, they are both the same element, right? But the problem is, in the reactant, not only you have cobalt 59, also you got neutron. So where is neutron? Neutron is gone. So you might say, okay, so since neutron's gone, okay, so part of the reactants has been changed. So although cobalt is still cobalt, all right. Oh, sorry, I missed that O. Okay, but that since that neutron from the reactant side disappears, so this is still an artificial transmutation. Okay, but of course, I don't think this is the best example to illustrate an artificial transmutation. Okay, if that's for me, I don't think this one is the perfect example, but it's okay. For the sake of argument, you could still say it's a transmutation. All right. So the other part of the equation is determine the nuclei. Okay, so everyone knows the nuclei produce. Okay, so the nuclei produced is cobalt. So that's only one thing is produced, right? Cobalt 60. All right. All right. So that will be it for this example. Okay. So that's another try by yourself. Okay. So this time, this one is from plutonium 239 to be bombarded with a small particle to produce curium 242. You need to identify the small particle used for the bombardment reaction and write the full nuclear reaction. Okay, again, you need to visit the periodic table, and also you need to. That means you need to get the atomic number for both elements. Okay, and then you write the full nuclear reaction. By balancing the mass number and the atomic numbers, then you will find out what the small particle is. Okay, so again, that's homework, and also you need to take photo to the folder, to the homework folder. I need to write that every time. Okay. Alright, so let's see another one. Okay, so about this one. Okay, so here comes our famous Einstein's equation, mass energy equivalence. Okay, so first we need to talk about a little bit history, a little bit background, why Einstein got the idea. Okay, so we know that during any nuclear transmutation, artificial and natural, a lot of energy, nuclear energy is released. Okay, in terms of the kinetic energies of emitted particles, such as alpha and beta particles, or as electromagnetic radiations, such as gamma rays. Okay, so there must be energy release, but the problem is, where comes this energy? Okay, so because we know in the universe, the law of conservation of total energy must be applied. Okay, so if there's something released energy, there must be a source of the energy, right? Okay, so and when they look into the nuclear transmutation, they find that for any nuclear transmutation which occurs either naturally or artificially, the total mass of reactant is, okay, so you need to think about this. Okay, the total mass of the reactant is what's bigger than or smaller than the products? Okay, the answer is greater. Okay, so that's very important point. So that's really important, so I need to highlight. The mass of the reactant is always greater than that of products. Okay, so or you might say the mass of products, the total mass of the products must be smaller than the mass of reactant. So for all this nuclear transmutation to happen, there must be a decrease in the mass of parents, okay, when they become daughters. Okay, the change in mass will have a special name. It's called mass defect. Mass defects. That means a decrease in the mass, actually. Okay, and Einstein relate that mass defect and also the energy emitted by using this formula. Okay, relate the mass defect and the energy released by the famous equation delta E equal delta M times C squared. Okay, so delta E means energy release. In this case, energy released. Okay, and delta M means mass defect. Okay, and how about C? C is the speed of light. Okay, so you might use 3 times 10 to the power 8 meter per second. That's a common, that's a very common constant for physics. But to be more precise in this chapter, you might use 2. Okay, I need to check because sometimes I might forget a few digits. Okay, so you might use this one instead. So 2.99792 is much is a more precise version. Okay, so how come Einstein get this equation? So that's a very long story, very complicated story. It relates to his famous theory called relativity. So this one's from the theory of relativity. So we are going to learn that theory of relativity in our unit 4. That means next year. Okay, but it just has a glimpse of the wisdom of Einstein, right? All right. Okay. So remember this formula. We are going to use this from very often from now on. Okay. Okay. So let's go to the other page. Okay, so for example, if I know how so like 5 times 10 to power 20 minus 28 kilogram of mass convert into energy. So we convert that mass into energy. Why? Because just like when we talk about nuclear reaction, from parents to daughter, parent lost some mass, and that's the loss of its mass becomes the energy um, of the possibly the particles they emitted, right? Okay, um, so we can always relate mass loss in mass or mass defects with energy. Okay, so how much energy in joule or megaevo is released if okay that amount of matter convert into energy. Okay, so that means you need to convert mass into energy, right? Okay, so we're going to use this particular. All right, okay, let's see. Delta m is, so why don't we use m rather than delta m? So because use delta m to emphasize that's the change in mass or the loss in mass. Okay, if you just use mass, sometimes it's confusing, right? Okay, so that's mass. Okay, so that's such a small mass, small amount of mass, right? But C, may I use this constant, right? Okay. You don't need to worry in the examination. You'll be given all the constants, all right? And let's see if we calculate this one. You will have, okay, if the calculation is right, have this one. Okay, so you see the mass is such a small mass and the energy is still small, but okay, it's to minus 11. Is when you compare with minus 28, minus 11 is much bigger, right? Okay, but that's in joule. Can we convert that into megaevo? Okay, remember 1 evo equals 1.0607 times 10 to the power minus 19 joule. Okay, so now if I want to convert something in joule back into evo, what I'm going to do? Okay, from evo to joule, you multiply, that's 1.607 dot dot dot. Okay, but going back, you are going to do division, right? So we might say delta E, if we are going to use evo, we are going to use 4.5 times this one, which is the energy in joule, divide by this one, by, okay, by the constant that converts evo into joule, but you divide it, so you will convert that back into evo. That makes sense? Alright, hopefully. Alright, so when you do that, you will see 2.8 times 10 to the power 8 evo. Okay, but the question is about megaevo. So we know megaevo, 1 megaevo equals 10 to the power 6 evo. Okay, so when you try to change evo into megaevo, so you need to divide that by 10 to the power 6, right? So again, I divide that by 10 to the power 6, and this one changed to megaevo, and that's 10 to the power, okay. Alright, so there we do it, because 8 minus 6 is 2. Okay, so that's the energy in terms of megaevo, so you answer the question. Alright, okay, so here another question, try yourself. Again, please do it as homework and photo to homework folder. Thank you. Okay, that's all for today's lesson. So what we have learned here, okay, So let's see, use the electron volt. So that part we have learned. So you need to assess yourself how much you understand. Recall that an isotope can be intentionally changed to another isotope by bombarding it with another particle in a process called artificial transmutation. Yep. Explain that in any nuclear reaction, the sum of masses of reactants will not equal to the sum of masses. Okay, the difference, mass difference. Okay, will not equal actually is not better than, less than. Okay, so less than would be stronger and more precise actually, because the masses of reactants, the sum of that masses will be less than the sum of masses of the products. Okay, understand that nuclear reaction will not produce naturally required energy. Sorry, we haven't learned that. Okay, and also we have learned parts of this equation, but we haven't learned the binding energy. Next video will be about binding energy. Okay, see you next time. All right, that's it.